Welcome to this video lesson. We're going to cover equations of simple harmonic motion, including kinematics and energy. Let's review the concepts of simple harmonic motion first. So we have an object here which is attached to a spring set. The spring is currently fully stretched, meaning that there's a net force from the spring pulling it to the left. Net force and acceleration in this case are proportional, meaning the acceleration is also in the negative or the left direction. The acceleration is going to pull the object in the left direction, meaning that the acceleration is left, velocity is going to be in the left direction, and since acceleration and velocity have the same direction, it's going to speed up in the left direction. Now the position is still positive because it's to the right of the equilibrium position, where position is going to be positive. It's going to speed up in this direction, but in the negative direction because it's moving to the left up to the point where it gets to the equilibrium position, and that's usually quarter of a period. Right after that point, it still has some momentum moving to the left, but now the spring is compressed, meaning it's going to be pushing the object to the right direction, meaning the acceleration changes from the left direction to the right direction, and we see that right over here. Since now velocity is to the left, but acceleration is to the right, so they have opposite signs, it means that the velocity is going, or the speed is going to decrease. So we can see the speed decreases up to the point where it gets to the zero, where it gets to the amplitude right at this point. We see that during this section of the movement, the object has a negative displacement because it's to the left of the equilibrium position. Once it reaches here, the spring is now fully compressed, meaning it's still putting a force in the positive direction. So we can see that in this region the force is still positive. It means that the acceleration is still to the right, and because the velocity at the beginning is zero, it's going to push the object to the right, so the velocity goes to the right now, and it is currently still in the negative displacement section because it's to the left of the equilibrium position. So we see that over here. And it's going to speed up. It's going to speed up to the time that it reaches its maximum speed right at the equilibrium position. And now we've hit the 3/4 of a period or oscillation. At this point over here, it's got some momentum. It still moves to the right. It's moving to the right, so velocity is positive. But now the spring is stretched, and since it's stretched, it's going to be pulling the object to the left direction based on the force. Since the net force is to the left, acceleration is to the left. We see that over here. Velocity and acceleration have opposite signs, so it's going to be slowing down, and we see that over here where the speed is reaching zero, and at this point over here it's to the right of the equilibrium position, meaning displacement is positive. All right, let's come up with equations of motion, and let's start with the position time. In this specific case, we're coming up with an equation where the motion starts at the amplitude position. So another way of representing this is as such. We have a wheel over here, and this wheel can rotate right to left. At this point in the wheel is attached to this little section, and this section can only travel up and down. So this is like a piston in a way. It can move up and down, and at this point over here, as it is at its maximum position, all the way to the top. And in this case, it's rotating clockwise, so it's going in here. So about quarter of a turn later, or quarter of its oscillation, we can see that it moved down. How much did it move down by? Well, the radius here is the amount that it moved on, or moved at. And this distance over here is really the amplitude, so we can label that over here. So after quarter of a turn, it has now reached the equilibrium position. So we can see that over here as well. So that's a quarter of the oscillation. And then a quarter later, it goes all the way down. So basically another amplitude, because that's the radius. And I'm going to label the radius as well here. And that radius is really the amplitude that's the amplitude of oscillation. So we see it over here is now at the negative displacement, which is equal to, in terms of magnitude, to the amplitude, and then it's rotating, it keeps rotating, so at this point it comes back to the equilibrium position, and then it comes all the way back up to here, which is the amplitude again. Now this wheel is going to be rotating at some angular velocity, and angular velocity is defined by how much angle is being covered per unit time. And we can calculate it, or we can find the angular speed by figuring out how many radians are being traveled within a specific oscillation. In this case, in one oscillation, you travel 2 pi of a period. So I'm going to write that in. So that's the total amount of radians over the amount of time that's taken. And the total amount of time that's taken is 1 whole period. Now that we know what angular speed is, let's try to come up with an equation for this graph. So we know that this is some sort of sinusoidal graph. We know that the starting position here is the amplitude, so that would be a cosine graph. So my equations start off by saying, okay, my displacement is going to equal to my amplitude multiplied by cosine of some sort of angle. And we got to figure out what goes in this bracket. Well, the x-axis here is t, or time, and in order to fulfill the entirety of one oscillation here, or one oscillation in which we cover the entire cosine graph, which starts with 1, goes to -1, and it comes back to 1, we have to travel 2 pi radians, and the amount of time it takes for that is the period. So that's kind of our equation, actually. So at time 0 over here, if I plug that into here, we get this entire thing becomes 0. Cosine of 0 is 1, and that would mean our displacement at time 0 is going to equal to x naught times 1, which is just x naught, or the amplitude, and that's correct for time 0. At time of 1/4 of a period, we plug in 1 over 4 times the period here. The t's cancel out. We're left with pi over 2. Cosine of pi over 2 is 0, and that would mean that the position at time of quarter t is equal to x naught times 0, which is 0, which is exactly what we get. We can do this for other time periods as well. For example, at a time which is half of the oscillation, or half of the period, if you plug in 1/2 of the period here, the periods cancel out, the 2's cancel out, and we are left with cosine of pi, which is -1, and the amplitude times -1 is negative of the amplitude, and our position at that point is exactly that. So the equation works really, really well in that sense, and we can rewrite this equation as well. And instead of writing it in terms of period, which we can always write it in terms of period, there's no problem with that, an alternative way of writing it, because 2 pi over period often represents the angular velocity, we can just write it as such, so that we don't have to write the 2 pi over period every time. Now, let's talk about what happens if this starts rotating faster. So what happens if the angular velocity here actually increases? If it increases, it would mean that this particle, if it was moving at a certain period, if this is moving faster, the period here is going to shorten, because this is going to start going up and down a lot faster. This makes sense within the equation sense as well, because if the period here decreases, based on this equation, the angular speed will increase. And as that period shortens, or if that angular velocity increases, let's say that we have omega is being multiplied by a factor of 2, that would mean that the period is being divided by 2. And the way to graph that now, that would mean that within the same period, instead of having one oscillation, we're now going to have 2 oscillations. and the graph will look something like this. And this is basically what another way of thinking about it is that, okay, if we're moving this faster, if it's rotating faster, it would mean that we're going to get more oscillation per unit time. Now, if we increase the angular velocity, it means that this is going to rotate a lot slower. And when it's rotating slower, it means it's going to take twice as long for the whole oscillation to occur. So if we decrease the angular velocity by a factor of 2, the period increases by a factor of 2. And when we're plotting this, it means that we're not going to get one entire oscillation anymore. We're just going to get half of an oscillation. And just to summarize here, the faster the oscillation, the more frequency we're going to get, and the slower it is, our frequency is going to decrease and the period is going to increase quite a bit. And this is the equation that we use if our starting position is right at the amplitude. So our equation, if the object starts at an amplitude or positive amplitude, it becomes cos x naught cos omega t. And if it starts at the equilibrium position, it's sine omega t, assuming that it starts moving in the positive direction first. To combine these two into one equation, we can write it as the position is equal to the amplitude multiplied by sine of omega t plus a horizontal phase shift. That phase shift is quite useful because let's say we have a sine graph here, so that's a sine graph. Starting position is at the equilibrium position, and if I want to shift this by pi over 2, I can go from a sine graph to a cos graph. So I have that option, and this equation with the horizontal phase shift gives me that option. So now that we have an equation that explains where the position of the particle is at all times, we can figure out what the velocity is as well. And we have to use a little bit of math here. So we know that velocity is the derivative of the position with respect to time. And if we take the derivative of this function, we have a constant here. We have a constant angular velocity because the period is also constant here. And for this, I'm not going to go through the math. We do need to use the product rule and a chain rule here. And we'll end up getting x naught times the derivative of the inside, which is omega, and the derivative of cosine, which is negative sine omega t. And I'll just rewrite that here in another form. It looks as such, and we can do it for the other side as well. And once I do the calculus, I'll end up getting omega x naught cosine of omega t. We can combine these two equations, and instead of writing it for starting position at amplitude and equilibrium, we can include a phase shift and write it as omega x naught cosine of the angular velocity times the time plus a phase shift. There's also a very clever math that we can do. Maybe I'll cover it at the end of this video for anybody who's interested, where we can combine this equation and this equation together and apply some very interesting math to get that the speed is equal to plus or minus the angular velocity, or 2 pi over t, multiplied by the square root of the amplitude squared minus the position squared. And where this becomes extremely helpful is that this equation is writing the velocity based on time. So basically, wherever, if you have a position time graph, you can use this equation to figure out what is the velocity at any point. However, if you have a position graph and if you end up having the period, then you can just use this equation and you can find the velocity at any position. Finally, acceleration is the derivative of the velocity with respect to time, or the slope of a tangent of a velocity time graph. And if we do this, we will end up getting, it's a sine graph, so negative omega squared x naught times the cosine of omega t. And interestingly enough, wait a second, amplitude times cosine of omega t is just x. So I can rewrite this as acceleration is equal to negative omega squared times x. If I do this with the other equation, I will get the exact same thing actually. So I will get negative omega squared x naught sine omega t. So that's in terms of time. However, x naught sine omega t in this case is also the displacement. So this ends up being omega squared x. And these two are pretty much the same thing, meaning that our acceleration is equal to negative the angular velocity squared times the displacement. And if you remember from the first video, we talked about the concepts of acceleration being proportional to the displacement. Well, this is the proportionality factor. So acceleration here is proportional to negative x. And if I take this, if I were to graph the acceleration and displacement, my slope will represent omega squared. Another important idea over here is that we know that the velocity is highest at the equilibrium position. So at the equilibrium position, the position here is going to equal to 0. So if I want the max speed, I'll write it as max speed. Vmax will equal to the time where this value is 0, so it becomes speed is equal to the angular velocity multiplied by the square root of the amplitude squared, which is just the amplitude. And this is how we can find the maximum speed of the particle. Now, this object, or the particle that's undergoing simple harmonic motion, it doesn't have a constant velocity, it doesn't have a constant acceleration either. So sometimes it's useful to find the average speed of the object as well. So average, or the mean speed, can also be calculated, and we can write that as such. And we know within one whole oscillation, the object moves up by one amplitude, it comes back by one amplitude, it goes down by one amplitude, and it goes back to the equilibrium position. So it travels a total distance of 4 amplitudes in a time of 1 period for that oscillation. And this gives us the average speed of the particle. I want to emphasize again that these equations are all about one specific particle and how is their position, velocity, and acceleration changes with respect to time, and how their velocity and acceleration changes with respect to position. This has nothing to do with wave speed, which we're going to cover a little bit later. This is all about one specific particle. Let's talk about energy equations. So we talked about the concepts of energy in another video, but we know that the kinetic energy is always converted into potential energy, and potential energy is converted to kinetic energy, and the addition of both of those two always leads to the total energy. We have now developed an equation for the velocity of the object, and I have a separate video explaining why this is the case, where velocity is equal to the angular velocity multiplied by the amplitude squared minus the position squared. But we can use this idea to develop the kinetic energy equation. So write that with pink. Ek is equal to 1/2 mass times velocity squared, and that is the kinetic energy of the particle at any point. So for the velocity, instead of using v, I'm going to use omega amplitude squared minus position squared. This would mean that this is 1/2 mass omega squared amplitude squared minus position squared all squared, and it ends up being 1/2 times the mass times angular velocity squared times amplitude squared minus position squared. And this is my kinetic energy of the particle at any position. In these situations, you almost always have the position of the object, and you have the amplitude, which is constant, you have the period, which is constant, and from that you can find omega, and therefore you can find the kinetic energy, and you should have the mass if you want that kinetic energy. Now, if you remember, the total energy of the object actually never changes, so the total energy is always the same. And if we look, the kinetic energy here is the highest when the object is at the equilibrium position. That's when it's going the fastest. So I can figure out what the total energy is, and that's when the kinetic energy is at the position of 0. So for total energy, we know that it happens when the position is at the equilibrium position. So this is, we can find that as ET is equal to 1/2 mass times the angular velocity squared times the amplitude squared minus the position here, which is 0 squared. And that's when the kinetic energy is at its maximum, and that's equivalent to the total energy at that point. So therefore ET will equal to 1/2 times mass angular velocity squared amplitude squared. Finally, to derive the potential energy equation, I'm going to choose a different color. We got potential energy is equal to the total energy minus the kinetic energy. That much we know because the total energy is the addition of the potential and kinetic energy. The total energy is 1/2 m omega squared amplitude squared, and the kinetic energy is 1/2 mass omega squared amplitude squared minus position squared. We can factor out the 1/2 m omega squared, and we'll end up getting x naught amplitude squared minus amplitude squared plus position squared. And putting all those together, these two cancel out, and we're left with 1/2 mass times the angular velocity squared times the position squared. And this is the equation for our potential energy of the particle at any position. One other idea that we covered in the past conceptually was the idea that the total energy of the particle is proportional to the mass of the object, the frequency squared, and also the amplitude squared. And we can see that from this equation over here. So the total energy, if we keep the angular velocity and the amplitude the same, if we increase the mass, the energy also increases, and we can see that they're directly proportional. In terms of amplitude, it's amplitude squared. So if we keep everything else similarly, if I increase the amplitude by a factor of 3, then the total energy changes by a factor of 3 squared. So it increases by a factor of 3 squared, or 9 times. Finally, frequency here. Now this is something that we know that the angular velocity is equal to 2 pi over period. We can also write this as angular velocity is equal to 2 pi times the frequency. So angular velocity is proportional to the frequency in this specific case. So these two are really proportional, meaning that if we increase the angular velocity by a factor of 3, for example, frequency also increases by a factor of 3. And that would mean that the total energy increases by a factor of 3 squared, or 9. So when we were doing the video on the energy concepts, we talked about all of these, but we didn't really have a solid foundation as why is it proportional to mass, frequency squared, and amplitude squared. And in this equation now gives us the idea as to why that is. As scientists, a lot of times we have certain intuitions that certain things happen and certain things should happen based on those changes. But again, it takes sometimes the mathematical tools. We use math as a tool in order to really understand the details of our intuition. Let's end up this video with a quick example. We have a wave here. This is the initial wave that I introduced in the very first video. I just gave it a little amplitude, so we got amplitude of 0.4 here. And we're going to come up with a position time function for this. What is the maximum speed? What is the acceleration at 0.9 second? What's the total energy? What's the potential energy at 0.9 second? And what's the kinetic energy at that time? Now would be a good time to pause the video and kind of go try the questions on your own first. And once you're finished, you can kind of check the answers. The first thing we're going to do is figure out what the period is. We know what the amplitude is. So the amplitude here is 0.4 meters. And everything is given in fundamental units already, which is nice. We don't really have to do any conversion. You have to be very careful when you're doing your assessments, because a lot of times it could be that a particle is moving much faster, so we sometimes give the unit as milliseconds, and a lot of time the oscillation is not that much, so we might give it to you as millimeters or centimeters. In this case, the period is 0.8 seconds. First, let's come up with the position time equation. So we got x is equal to the amplitude times, here the starting position is 0, 0. So I'm going to use the sine function here. And instead of omega, I'll actually use 2 pi over the period times t. And x, we do have this value as 0.4. This is going to be sine. Here we got 2 pi over 0.8 t. And we end up getting x is equal to 0.4 sine 2.5 t. And the unit for this will be in meters. For the velocity, well, we know velocity is, or maximum speed here, is omega square root of x naught squared minus x squared. Again, we know that the maximum speed happens at the equilibrium position. That's when it's going the fastest, meaning that the position is going to be 0 when we want to figure out the max speed. So this is going to be plus or minus. We want the speed in this case. We don't really care about the negative sign. So V max will equal to omega here, which is 2 pi over the period. Again, that's 0.8 multiplied by the square root of the amplitude squared, which ends up being 0.4, Putting everything together, we get the speed as pi meters per second. If you want to write this properly in proper number of significant digits, you need to see exactly what the numbers are given as. In this case, let's imagine that everything is given in 2 significant digits. So this is going to be 3.1 meters per second. I'm just rounding 3.14159. Continued on with many different digits as to 2 significant digits. Before finding the acceleration, potential energy, and kinetic energy, I'll just do the total energy as well because I have all the information for it. So for total energy here is going to equal to 1/2 times the mass times omega squared times the amplitude squared. So I have half the mass is 250 grams. Here that's 0.25. That's important. You have to make sure the mass is given or the mass is changed to fundamental units. We got omega squared, which is 2 pi over 0.8 squared, and the amplitude is 0.4 squared. Plugging all those into a calculator, I get 1.2337 joules, which the 2 significant digits is approximately 1.2 joules. For all the other variables that we need to find a whole bunch of information at 0.9 seconds. And all of these variables are kind of dependent on what is the position at that point. So the first step into finding the acceleration, potential energy, and kinetic energy at those points would be to find the position. The position is 0.4 times sine 2.5 pi times 0.9 seconds. We got to remember that our calculator needs to be in radians. We're working in radians here. We end up getting position is equal to 0.2828. We need that exact value for future, so it's a good idea to save it on your calculators. It's always a good idea to check to make sure that you are on the right track. So basically here at 0.9 second, if I look at my position time graph, first of all, my position is positive and it's positive here, so that's good. And if I go up and go all the way here, I'm somewhere between 0.2 and 0.4, and that's my position here, so it looks like I'm on the right track. Now to calculate my acceleration is equal to negative omega squared times the displacement. That's negative 2 pi over 0.8. Could just write it as 2.5 pi as well, times the displacement, which is 0.28. Again, we have to use the exact value. And we'll end up getting negative 17.447. I'm going to round it to 2 significant digits here, so negative 17 meters per second squared. Just to check here, our displacement is positive, acceleration is always towards the equilibrium position, so it should be negative whenever position is positive, so at least it checks that part. So I'm on the right track here. And 17 meters per second squared, nothing too unreasonable. Potential energy at this point, potential is equal to 1/2 mass omega squared times position squared, and that will equal to 1/2. The mass is 0.25. Omega squared is 2 pi over 0.8. I'll just write 2.5 pi here. And position here is the 0.28 squared. And I will end up getting 0.61685 repeated, which is approximately 0.62 joules. Now, does the answer make sense? Well, we're halfway between the equilibrium position and the amplitude, so we should have about half the total energy, and the total energy is about 1.2337, and this is 0.616, which is exactly half, so fantastic. This is already leading us to the final answer over here, because if half of it is potential energy, it means the rest of it is kinetic energy. So kinetic energy here, we can use the equation, or we can just write EK is equal to the total energy minus the potential energy at that point. And we're using the same times here, so that's 1.233 minus 0.616, and when we do this we get 0.6168 again, which is approximately 0.62 joules. And again, you could have done this just by knowing that it's halfway there and it's half the energy. You could have done that for both the potential energy and the kinetic energy, having known what the total energy is, but it's good practice to kind of check the answers. I hope this video gave you an idea about how these equations are derived and how they could be used. I hope you have a wonderful day. Thank you for watching.